Welcome to Tech Observers. Black holes might easily be one of the most compelling mysteries in the universe. These are the famous objects in space that no matter or radiation can escape. The gravitational pull of these objects is so large that even the fastest thing in our universe, light, cannot escape it. Because of this, black holes are the darkest objects in our cosmos. They are the result of large dying stars that collapse in on themselves. All the masses is squeezed into a very small amount of space. Whilst the core of the star is imploding, the outer layers are flung out into the space in the form of a supernova, a beautiful cosmic explosion. Supernovae are also the reason why heavier elements are seen in our world. Without supernovae, we would not exist. You have probably heard this before, but yes, this is where the saying "we are stardust" comes from. But it won't be wrong to say that black holes are tricky to find. They cannot be detected because they suck all the surrounding light in and do not emit any detectable radiation. Instead, scientists will look at the effects of the strong gravitational pull of the black hole on the surrounding space. As far as we know, black holes are so dense that nothing can escape their event horizon. But they're not the only type of hole out there in space. Let's say you're tinkering around with numbers exploring the space-time around a black hole, and you subtract that collapsed star, all the actual matter and mass from your calculations. What the remaining math describes is something called a white hole, a massless singularity. As the name implies, a white hole is the opposite of a black hole, and astrophysicists have been playing with the concept since the 1970s. While a black hole's event horizon is the boundary at which its gravitational strength prevents even light from reaching escape velocity, a white hole's event horizon prevents anything from entering. You can't escape a black hole. You can't go into a white one. So, where a black hole is sucking matter in, a white hole is spewing it out. They would be incredibly white and incredibly energetic, hurling radiation into space at a furious rate. Hypothetically, it would be like hitting a rewind button on a black hole. According to Eric Curiel, writing for the Stanford Encyclopedia of Philosophy, because the field equations of general relativity do not pick out a preferred direction of time, if the formation of a black hole is allowed by the laws of space-time and gravity, then those laws also permit white holes. We have never, to our knowledge, actually observed a white hole. Physicists think they are not likely able to exist in the universe, and there are several reasons for this. One big question is, how would they form? We have plausible models of how black holes form, but it's not as if we can actually rewind time in the universe to turn them into white holes. For this to happen, you would have to start with the singularity and then go backwards. Then the object that would be out there would vomit up matter until it assembles itself back into a star. Then also that would require a decrease in entropy, which would in turn violate the second law of thermodynamics. When Stephen Hawking proposed the idea that a black hole will eventually evaporate, leaking radiation from its event horizon, there was a problem. If it evaporates, what happens to all the information it sucked in? If quantum theory is correct, this would defy a fundamental law that information cannot be lost. It's called the no-hiding theorem. With the no-hiding theorem, if information is missing from one system, then it simply means that it must be residing somewhere else in the universe. A classic cosmic game of hide and seek. So theoretically, if information is getting sucked in, it must be getting spat back out somewhere, and likely that's through a white hole. But is it possible that white holes exist? One way to conceptualize this in a very basic mathematical sense is to think about the square root of 9. The answer is both 3 and -3. This is fundamentally part of what's known as Schwarzschild's geometry, the formula used in general relativity to describe the gravitational field outside a spherical mass. Just like the color black is the opposite of white, the white hole is the opposite of a black hole in every possible way. Light cannot escape a black hole, so light cannot enter a white one. This would obviously make a white hole incredibly bright, and some quantum physicists believe that maybe some of the light in the universe we thought was coming from supernovas may actually be from white holes. Physicists also believe that this concept could be germane when talking about the Big Bang and how our universe came into existence. They believe it's possible that at the moment of creation, everything was expelled from a massive white hole on an incredibly large scale. The premise of white holes is based on a theory that space-time is made of granular building blocks that can be quantified. This quantification comes in the form of loops, almost like little threads that are of finite size, so finite they cannot be subdivided any further. To a viewer, these loops would make space-time appear to be smooth and continuous, but their granular nature would prevent highly dense bodies like neutron stars from collapsing into a point of infinite density. So, in the case of black holes, these incredibly finite loops would prevent a collapse into infinity, but eventually the loops would only be able to compress to a certain point until they exert an outward pressure almost like a spring. This is referred to as a quantum bounce, a rebound from a black hole ingesting everything into a white hole expelling everything. Now, many might argue that white holes are theoretically impossible because they violate the second law of thermodynamics, stating that entropy cannot be decreased in a system, but it depends on how one looks at entropy, with some physicists saying it refers to disorder, while others say it refers to information used to describe a system, and an argument over semantics ensues. In fact, the term Big Bang might be somewhat misleading in this regard. According to the current mainstream theory, the universe didn't explode into existence from a single point. It inflated into existence and spent 500 million years or so in darkness, not really expanding much before the intergalactic medium ionized and the light switched on. That's not hugely consistent with a white hole model. But wait, there's more. There is a hypothesis that a white hole is what a black hole turns into at the end of its lifespan. Black holes seem pretty long-lived, so it's possible that the universe hasn't been around long enough for the evolution of a white hole to take place. Or maybe it has, and the white holes wink out of existence even before we are able to see them. Meaning that it's only tiny primordial black holes that have turned into tiny white holes, which now constitute a component of dark matter. These are all mathematical possibilities, but it's the real universe in which we are actually living in, and not the realm of pure mathematics. White holes and wormholes. So, if a black hole is sucking in all of this information and a white hole is spitting it out somewhere, must not there be something connecting the two? A wormhole perhaps? Maybe. The aforementioned Schwarzschild geometry necessitates a wormhole would connect a black hole and white hole with two separate universes connected at their horizons, also known as an Einstein-Rosen bridge. Unfortunately for us, these wormholes would be highly unstable if they were even possible. It would also be impossible with physics as we know it for one to pass through a wormhole into another universe, even theoretically, due to a number of pesky things like being spaghettified when passing through a black hole's event horizon before being compressed at the singularity. Though you might at least get to see some distorted light from the parallel universe on the other side. But since this is mostly theoretical, there are always theoretical solutions, like using exotic matter to stabilize a wormhole. Exotic matter has negative mass and positive surface pressure. This would keep the throat of the wormhole stable while also preventing it from collapsing. This would hypothetically allow for travelers to pass through. Well, in the end, I would like to leave you all with some questions to ponder over. Like, will we ever figure out if wormholes exist and whether they can be used for time travel or interdimensional travel? Or have we already? And if we have, then who is to say that the reality we are living in is a real one or just a parallel copy of the infinite number of other ones? As usual, thank you for watching our video. Do subscribe to our channel Tech Observers and click that bell icon for more interesting videos.